Imagine stepping onto the surface of Venus. Within 3 seconds, the 900-degree heat would cook you alive. The atmospheric pressure would crush your body like an empty can. The sulfuric acid in the air would dissolve your lungs before you could even scream. This is what happens when a planet dies, and it might be Earth's future. Venus wasn't always hell. 4 billion years ago, it might have had oceans, continents, maybe even life. Then something catastrophic happened. The greenhouse effect spiraled out of control. The oceans boiled away, and paradise became the most hostile place in the solar system. Today, lead melts on Venus's surface. The atmospheric pressure is 92 times greater than Earth's. The clouds are made of battery acid. But here's what's truly terrifying. Venus started out almost identical to Earth. Same size, same composition, formed in the same stellar neighborhood. The only significant difference was its distance from the Sun, just 30% closer. That small difference triggered a climate collapse so complete that it turned a potentially habitable world into literal hell. You're about to see the real Venus, not the artistic renderings or computer graphics you've seen online, but actual photographs taken from the surface, radar maps revealing active volcanoes, and thermal images showing a planet still glowing with its own heat. No CGI, no filters, just raw alien horror captured by machines that died taking these images. Welcome back to Space Prime, where we explore the most unsettling mysteries of our universe. Today, we're investigating Venus, Earth's evil twin, climate change's ultimate warning, and a world that shows us exactly what happens when planetary climate systems collapse beyond recovery. The hell world next door, Earth's evil twin. Venus should have been Earth's twin sister. When the solar system formed 4.6 billion years ago, these two planets condensed from the same cosmic materials in the same stellar neighborhood. They have nearly identical sizes. Venus is only 650 kilometers smaller in diameter than Earth. They have similar masses, similar densities, similar gravitational fields. In any reasonable universe, they should have evolved along similar paths. But something went catastrophically wrong. While Earth became a blue marble covered in oceans and teeming with life, Venus became the closest thing to hell that exists in our solar system. The surface temperature is 464 degrees Celsius, hot enough to melt lead, zinc, and tin. The atmospheric pressure is equivalent to being nearly a kilometer underwater on Earth. The air itself is mostly carbon dioxide laced with sulfuric acid clouds that would strip flesh from bone. This isn't just a curiosity for planetary scientists. Venus represents the ultimate climate change nightmare, a runaway greenhouse effect that once started, never stopped. Understanding what happened to Venus isn't just about exploring alien worlds. It's about understanding the future of our own planet as greenhouse gas concentrations continue to rise in Earth's atmosphere. The greenhouse effect that's warming Earth today is the same physical process that turned Venus into hell. Carbon dioxide traps heat from the sun, preventing it from radiating back into space. On Earth, this effect has been relatively mild so far, but Venus shows us what happens when greenhouse gases reach a tipping point, when the heating becomes so intense that it triggers feedback loops that spiral out of control. The terrifying parallel is that Venus might once have been habitable. Computer models suggest that early Venus could have had liquid water oceans for the first 2 billion years of its existence. It might have had continents, weather systems, maybe even primitive life. Then the greenhouse effect began to accelerate. The oceans started to evaporate, adding more water vapor, itself a greenhouse gas, to the atmosphere. The surface got hotter, which caused more evaporation, which caused more heating, in a feedback loop that never stopped until every drop of water was gone forever. The Soviet death missions. In the 1960s and 70s, landing on Venus was considered nearly impossible. The Soviet Union tried anyway, launching a series of missions that reads like a catalog of technological disasters. The Venera program attempted to land on Venus 23 times between 1961 and 1984. Most missions failed completely. Spacecraft were destroyed by the hostile environment before they could transmit a single piece of data back to Earth. The engineering challenges were unlike anything space agencies had faced. How do you build electronics that can function at temperatures hot enough to melt lead? How do you create pressure vessels that can withstand atmospheric pressures equivalent to being crushed under a kilometer of ocean? How do you design cameras and instruments that can survive in an atmosphere that's essentially a pressurized sulfuric acid bath? The first successful landing was Venera 9 in 1975. The lander was built like a tank, a heavily armored sphere designed to withstand the crushing pressure and corrosive atmosphere. It was equipped with cooling systems, pressure-resistant housings, and instruments hardened against the most extreme conditions imaginable. The mission plan was brutally simple: survive long enough to take one photograph photograph and transmit it back to Earth. Venera 9 lasted 53 minutes on the surface before the hostile environment destroyed it. But in that brief window, it accomplished something extraordinary. It sent back the first photograph ever taken from the surface of another planet. The image was grainy, black and white, and showed a desolate landscape of flat rocks under a hazy sky. It wasn't beautiful, but it was real. This was what hell actually looked like. Venera 10 followed 4 days later, landing 2,200 kilometers away and surviving for 65 minutes. It sent back another haunting photograph showing cracked slabs of rock under the dim glow of Venus's acid-shrouded sky. The lighting was eerie, bright enough to see clearly, but diffused through layers of sulfuric acid clouds that filtered out most of the sun's direct light. The most ambitious Venera missions came in 1982. Venera 13 and 14 didn't just take photographs, they recorded sound, analyzed soil samples, and transmitted the first color images from Venus's surface. The sound recordings captured the muffled howl of winds moving through the dense atmosphere. The soil analysis revealed surface rocks rich in basalt, suggesting extensive volcanic activity, and the color photographs showed a world tinted yellow and orange by the sulfuric acid haze, a landscape that looked like it was perpetually on fire. These missions proved something important. Venus wasn't just hot, it was actively hostile. The surface wasn't a frozen wasteland like Mars. It was a dynamic, violent environment where the very air was poison and the ground was hot enough to glow. The Great Deception. From Earth, Venus is beautiful. It's the third brightest object in our sky after the sun and moon, appearing as a brilliant white star that ancient astronomers called both the morning star and evening star before they realized it was a single planet. Through telescopes, Venus appears as a smooth, featureless white sphere, elegant, pristine, almost angelic. This beauty is completely deceptive. What we're seeing isn't the planet itself. It's a thick blanket of clouds that completely obscures the surface. These aren't water clouds like on Earth. They're made of sulfuric acid droplets suspended in a carbon dioxide atmosphere so dense that the surface pressure is 92 times greater than Earth's atmospheric pressure at sea level. The greenhouse effect on Venus operates like a planetary furnace with the thermostat permanently stuck. Solar energy penetrates the atmosphere and heats the surface, but the dense carbon dioxide atmosphere prevents that heat from escaping back into space. The trapped energy keeps accumulating, driving surface temperatures higher and higher until they reach equilibrium at temperatures that would melt lead. What makes Venus's greenhouse effect so extreme isn't just the carbon dioxide concentration. Though at 96% CO2, the atmosphere is nearly pure greenhouse gas. It's also the atmospheric pressure. The dense atmosphere acts like a heavy blanket, trapping heat so effectively that the night side of Venus, which doesn't see sunlight for months at a time, is just as hot as the day side. This creates temperature conditions that are almost unimaginable. The surface of Venus is hotter than Mercury, despite being twice as far from the sun. It's hot enough to melt tin, lead, zinc, and aluminum. It's so hot that rocks on the surface actually glow with their own thermal radiation, a phenomenon that would later become crucial for imaging the planet's surface. The atmospheric composition tells a story of planetary catastrophe. The high concentration of carbon dioxide suggests that Venus once had much more water than it does today. As the greenhouse effect intensified, the oceans began to boil. Water vapor rose high into the atmosphere, where solar radiation split it into hydrogen and oxygen. The lightweight hydrogen escaped into space, while the oxygen combined with surface rocks. This process continued until every drop of water was gone, leaving behind the dry, toxic atmosphere we see today. Venus represents the ultimate climate tipping point, the point where greenhouse heating becomes so intense that it triggers irreversible feedback loops. Once Venus crossed that threshold, there was no going back. The planet was doomed to become the hell world we see today. Piercing the veil, the radar revolution. For decades after the Venera missions, Venus remained largely mysterious. We had a few photographs from the surface showing local rock formations, but the planet's thick cloud cover made it impossible to map the global topography or understand the large-scale geological processes that had shaped the world. Everything changed with the Magellan mission, launched by NASA in 1989. Magellan wasn't designed to take pretty pictures. Instead, it carried a sophisticated synthetic aperture radar system that could penetrate Venus's thick atmosphere and map the surface with unprecedented detail. Radar waves could pass through the sulfuric acid clouds, bounce off the surface, and return with information about terrain elevation, surface roughness, and geological structures. When Magellan reached Venus in 1990, it began a systematic mapping campaign that would revolutionize our understanding of the planet. The spacecraft spent 4 years methodically scanning Venus's surface, ultimately mapping 98% of the planet with a resolution as fine as 100 meters per pixel. What it revealed was shocking. Venus wasn't just geologically active, it was geologically catastrophic. The radar maps showed massive shield volcanoes larger than anything on Earth. Maat Mons, the largest volcano on Venus, rises 8 kilometers above the surrounding plains and spans 400 kilometers at its base. For comparison, Hawaii's Mauna Loa, the largest volcano on Earth, is only 120 kilometers across at its base, but individual volcanoes were just the beginning. Magellan revealed that Venus's surface was dominated by vast volcanic plains that covered 80% of the planet. These weren't ancient, eroded volcanic fields like we see on Mars or the Moon. Based on crater counting, a technique that measures surface age by counting impact craters, scientists realized that Venus's surface was geologically young, probably no more than 300 to 500 million years old. This discovery led to one of the most startling theories in planetary science: global resurfacing. At some point in Venus's recent geological history, the entire planet might have been resurfaced by volcanic activity. The old crust was buried under kilometers of lava flows, creating the relatively crater-free surface we see today. This wasn't gradual volcanic activity like we see on Earth. It was planetary-scale catastrophe that buried an entire world's geological history. The radar maps also revealed geological features that don't exist anywhere else in the solar system. Pancake domes, flat, circular volcanic structures up to 25 kilometers across, dotted the landscape. Tesserae terrain showed areas where the crust had been compressed, folded, and fractured in patterns that suggested incredible tectonic forces. Coronae formations, circular features surrounded by rings of ridges and fractures, indicated areas where hot material from Venus's interior had pushed up through the crust. What emerged from Magellan's mapping was a picture of Venus as a world dominated by volcanic and tectonic processes far more intense than anything we see on Earth. The planet wasn't just hot and toxic, it was geologically violent on a scale that challenged our understanding of how terrestrial planets evolve. Earth-based detective work. While Magellan was revolutionizing our view of Venus from orbit, another group of researchers was accomplishing something that seemed almost impossible: mapping Venus's surface from Earth using ground-based radar systems. The technique required bouncing radio signals across millions of kilometers of space through Venus's dense atmosphere, off the planet's surface, and back to receivers on Earth. The process sounds simple, but was incredibly challenging to execute. The Arecibo Observatory in Puerto Rico would transmit powerful radar pulses toward Venus. These signals would travel for several minutes through space, penetrate Venus's atmosphere, scatter off the surface, and return to Earth so weak they were barely detectable above background noise. The round-trip time for these signals was over 4 minutes, and by the time they returned, they carried information about Venus's surface topography, encoded in subtle variations in signal strength and timing. The technical achievement was remarkable. From a distance of 40 million kilometers, Earth-based radar could resolve surface features on Venus with precision comparable to orbital missions. The maps weren't as detailed as Magellan's close-up observations, but they offered something orbital missions couldn't: the ability to observe the same areas repeatedly over time and look for changes. This temporal capability led to one of the most important discoveries in recent Venus research. By comparing radar observations of the same regions taken years apart, scientists began to detect subtle changes in surface reflectivity that suggested ongoing geological activity. Some areas became more reflective over time, possibly indicating fresh lava flows. Others showed changes in surface roughness that could indicate collapse features or new volcanic structures. The most intriguing discoveries came from detailed analysis of specific volcanic regions. Idun Planitia, a vast plain dotted with volcanic features, showed changes between 2012 and 2020, observations that couldn't be explained by instrument noise or processing artifacts. The changes suggested that Venus's surface was still evolving, that the planet wasn't just geologically active in the ancient past, but might still be reshaping itself today. Ground-based radar observations also provided crucial validation for orbital missions. Areas that appeared rough in Magellan's radar scans also showed high reflectivity in Earth-based observations. Smooth plains like Sedna Planitia appeared similarly in both datasets. This cross-validation gave scientists confidence that both approaches were accurately revealing Venus's true surface characteristics. The technique became even more sophisticated with the development of bistatic radar observations. Instead of using a single antenna to both transmit and receive signals, astronomers began using separate facilities, one to transmit signals to Venus and another to receive the reflected signals. This approach improved sensitivity and allowed for more detailed analysis of surface properties. Unfortunately, the collapse of the Arecibo Observatory in 2020 dealt a significant blow to Venus radar research. Arecibo's large dish and powerful transmitters had made it uniquely suited for interplanetary radar observations. However, the work continues using other facilities, including NASA's Deep Space Network antennas and the Green Bank Telescope in West Virginia. The accidental discovery. In 2018, NASA launched the Parker Solar Probe on an ambitious mission to study the Sun's outer atmosphere. The spacecraft would make repeated close approaches to our star, enduring temperatures and radiation levels that would destroy most electronics. To reach these extreme solar orbits, Parker needed to use Venus for gravitational assist maneuvers, essentially using the planet's gravity as a slingshot to adjust its trajectory. These Venus flybys were purely utilitarian. Parker wasn't designed to study Venus, and its instruments were optimized for observing the solar corona, not planetary surfaces. The spacecraft's main camera, called WISPR, Wide Field Imager for Solar Probe Plus, was designed to photograph the Sun's outer atmosphere and solar wind structures. No one expected it to see anything interesting during the brief Venus encounters. But during Parker's third Venus flyby in July 2020, mission scientists decided to test whether WISPR could image Venus during the nightside passage. The results were completely unexpected. Instead of seeing nothing but the familiar blank face of Venus's cloud cover, WISPR captured images showing faint features on the planet's actual surface. The key was thermal emission. Venus's surface is so hot, 464 degrees Celsius, that it glows with its own heat at specific infrared wavelengths. WISPR's sensitivity extended into the near-infrared spectrum, allowing it to detect this faint thermal glow penetrating through the planet's thick atmosphere. For the first time in the history of Venus exploration, a spacecraft had captured visible light images showing surface features from orbit. The images revealed the familiar outlines of major geological features that had previously been mapped only by radar. Aphrodite Terra, Venus's largest highland region, appeared as a bright area in the thermal images. The contrast between highlands and lowlands was clearly visible, with different regions glowing at different intensities based on their temperature, composition, or surface roughness. What made this discovery so remarkable was its complete unexpectedness. WISPR was designed to look at the Sun's corona, one of the hottest and brightest regions in the solar system. The fact that it could also detect the faint thermal glow from Venus's surface was a testament to both the instrument's sensitivity and the extreme surface conditions on Venus. The thermal imaging also revealed atmospheric features that had never been seen before. WISPR detected a faint glow in Venus's upper atmosphere caused by oxygen atoms being excited by solar radiation, a phenomenon similar to Earth's auroras, but occurring through different physical processes. This airglow provided new insights into how Venus's upper atmosphere interacts with the solar wind and loses gases to space. Perhaps most importantly, Parker's accidental discovery opened up an entirely new way to study Venus. If a solar probe could image Venus's surface using thermal emission, what could dedicated Venus missions accomplish with instruments specifically designed for this type of observation? The discovery sparked renewed interest in visible light Venus exploration and influenced the design of future missions. The success also demonstrated how much the discovery sparked renewed interest in visible light Venus exploration and influenced the design of future missions. Don't know about Venus. Despite decades of exploration, the planet could still surprise us in fundamental ways. The thermal imaging revealed that Venus's surface features are visible from orbit if you know how to look for them, a capability that no one had realized existed until Parker Solar Probe stumbled upon it by accident. The living hell, volcanoes from hell. In 2023, researchers analyzing archival data from the Magellan mission made a discovery that fundamentally changed our understanding of Venus. While examining radar images of Maat Mons, one of Venus's largest volcanoes, they noticed something that should have been impossible. The volcanic vent had changed shape between two observations taken 8 months apart. The change was subtle but undeniable. In the first image, the vent appeared as a circular depression about 2 2 kilometers across. In the second image, taken during a later orbital pass, the vent was larger and less defined, with radar reflections suggesting that fresh lava had flooded the floor and the walls had partially collapsed. This was direct evidence that Venus wasn't geologically dead. It was still actively reshaping its surface through ongoing volcanic processes. This discovery triggered a systematic reanalysis of Magellan's complete dataset using modern image processing techniques and artificial intelligence algorithms designed to detect subtle changes in radar reflectivity. The results were startling. Researchers identified dozens of locations showing evidence of recent volcanic activity across Venus's surface. The scale of Venusian volcanism is difficult to comprehend. Maat Mons rises 8 kilometers above the surrounding plains and spans 400 kilometers at its base. Its volume is roughly 300 times larger than Hawaii's Mauna Loa, the largest volcano on Earth. But Maat Mons is just one of hundreds of major volcanic structures on Venus. The planet contains more volcanoes than any other world in the solar system. Over 1,600 major volcanic features have been identified, along with thousands of smaller volcanic structures. What makes Venus's volcanism particularly intense is the planet's thick atmosphere and high surface pressure. On Earth, explosive volcanic eruptions occur when dissolved gases in magma expand rapidly as pressure decreases during eruption. But on Venus, the extreme atmospheric pressure prevents this explosive expansion. Instead, Venusian eruptions tend to be effusive, producing massive lava flows that can extend for hundreds of kilometers across the surface. The chemical composition of Venus's volcanism also differs from Earth's. Spectroscopic analysis of the atmosphere shows elevated levels of sulfur dioxide and other volcanic gases, suggesting that Venus's magma contains high concentrations of sulfur compounds. When this sulfur-rich magma erupts, it releases massive amounts of sulfur dioxide into the atmosphere, contributing to the planet's toxic air and sulfuric acid clouds. Recent volcanic activity also explains some of Venus's atmospheric mysteries. Scientists have long puzzled over variations in sulfur dioxide concentrations in Venus's upper atmosphere, levels that seem to fluctuate over time in ways that couldn't be explained by atmospheric circulation alone. Active volcanism provides a perfect explanation. Fresh eruptions inject new sulfur dioxide into the atmosphere, creating temporary increases in concentration that gradually decline as the gas is processed by atmospheric chemistry. The discovery of active volcanism has profound implications for understanding Venus's interior structure. Active volcanoes require ongoing heat sources and magma production, suggesting that Venus's interior remains hot and dynamic. The planet likely has a partially molten mantle with convection patterns that drive continuing geological activity, a stark contrast to Mars, where volcanism largely ceased billions of years ago as the planet's interior cooled. The climate connection. Venus isn't just a geological curiosity. It's a cautionary tale about the ultimate consequences of runaway climate change. The planet serves as a natural laboratory for studying greenhouse effects under the most extreme conditions imaginable, providing insights that are directly relevant to understanding Earth's climate future. The parallels between Venus's ancient climate catastrophe and Earth's current climate trajectory are both striking and terrifying. Both planets started with similar atmospheric compositions and surface conditions. Both experienced greenhouse heating as stellar luminosity increased over geological time. The crucial difference was that Venus crossed a climate tipping point from which there was no recovery. Scientists believe Venus's climate collapse began around 3 to 4 billion years ago, when increasing solar luminosity pushed the planet's surface temperature beyond a critical threshold. Once surface temperatures reached the boiling point of water, Venus's oceans began to evaporate rapidly. Water vapor is itself a powerful greenhouse gas, so the evaporating oceans created a feedback loop that accelerated the heating process. As more water evaporated, the atmosphere trapped more heat, which caused more evaporation, which trapped even more heat. This runaway greenhouse effect continued until Venus's oceans were completely gone, boiled away into space over the course of millions of years. Without liquid water to moderate temperatures through evaporation and weather patterns, Venus's surface temperature continued rising until it reached the hellish conditions we see today. The loss of Venus's water wasn't just a climate disaster, it was a complete sterilization of the planet. If Venus had ever harbored life, that life would have been extinct within a relatively short geological time frame. The planet went from potentially habitable to completely sterile in what amounts to a cosmic instant. Current climate change on Earth operates through similar physical mechanisms, though at much smaller scales and slower timescales. Increasing concentrations of carbon dioxide and other greenhouse gases are trapping more heat in Earth's atmosphere, driving global temperature increases that are already causing significant environmental changes. While Earth is nowhere near Venus's extreme conditions, the underlying physics are identical. What makes Venus particularly relevant to climate science is that it demonstrates the ultimate endpoint of greenhouse heating. Venus shows us what happens when greenhouse gas concentrations reach levels that trigger irreversible feedback loops. The planet serves as proof that terrestrial worlds can undergo climate changes so extreme that they fundamentally alter the planet's habitability. Venus also provides insights into the role of atmospheric pressure in greenhouse heating. Earth's atmosphere is roughly 100 times thinner than Venus's, which means that even significant increases in greenhouse gas concentrations won't create Venus-like conditions in the foreseeable future. However, Venus demonstrates that atmospheric density can amplify greenhouse effects beyond what simple gas concentration models might predict. The study of Venus's climate history also reveals the importance of water vapor as a greenhouse gas. On Earth, water vapor concentrations are controlled by temperature. Warmer air can hold more moisture, creating the potential for feedback loops similar to what occurred on Venus. Understanding how water vapor feedback operates on Venus helps climate scientists refine their models of how similar processes might affect Earth's future climate. Decoding the real images. When most people search for Venus images online, they encounter beautiful artistic renderings showing a smooth, cloud-covered world with dramatic orange and purple hues. These images are striking, but they're not real. They're computer-generated interpretations or heavily processed composites designed for aesthetic appeal rather than scientific accuracy. The actual photographs and data from Venus tell a much harsher story. Let's examine what you're really looking at in genuine Venus imagery, starting with the most famous and historically significant images, the surface photographs taken by Soviet Venera landers. The Venera surface images are among the most extraordinary photographs in the history of space exploration, not because they're beautiful, but because they document the most extreme planetary environment ever directly observed. These grainy black and white panoramas show flat expanses of broken rock under skies dim with sulfuric acid haze. The rocks themselves appear layered and fractured, likely formed from basaltic lava flows that cooled and cracked under Venus's extreme atmospheric conditions. What makes these images particularly haunting is their context. The cameras that took these photographs were dying while they recorded them. The extreme heat and corrosive atmosphere were actively destroying the electronics and mechanical systems even as they operated. Each image represents a moment captured in one of the most hostile environments in the solar system, a place where the very air is poison and the ground is hot enough to glow. The color images from Venera 13 and 14 add another layer of alien strangeness. The yellow and orange tints aren't artistic choices. They're the actual colors of Venus's surface lighting filtered through an atmosphere of carbon dioxide and sulfuric acid. The sun's light reaches the surface, but it's scattered and absorbed by atmospheric particles in ways that create an eerie, perpetual twilight. The lighting resembles being underwater, with diffuse illumination coming from all directions rather than direct sunlight. Magellan's radar maps represent a completely different type of image. These aren't photographs in any conventional sense. They're radar reflections converted into visual data. Bright areas indicate surfaces that strongly reflect radar waves, typically rough terrain like volcanic slopes or fractured plains. Dark areas show smooth surfaces that absorb or scatter radar waves, usually indicating lava flows or sedimentary plains. When you look at Magellan's radar images, you're seeing Venus's topography revealed for the first time. The massive shield volcanoes appear as bright circular features with dark flows extending from their bases. The tesserae terrain shows up as complex patterns of bright ridges and valleys where the crust has been folded and fractured by tectonic forces. The pancake domes appear as perfectly circular bright spots scattered across the volcanic plains. Parker's Solar Probe's thermal images represent yet another way of seeing Venus. These images show the planet glowing with its own heat, thermal radiation from rocks so hot they emit visible light. The bright areas in these thermal images correspond to highlands that are slightly hotter than surrounding areas, while darker regions show cooler lowlands. What you're seeing isn't reflected sunlight, but the actual thermal glow of an overheated world. The key to understanding Venus imagery is recognizing that each type reveals different aspects of the same hellish reality. Surface photographs show local conditions, the rocks, lighting, and atmosphere at specific landing sites. Radar maps reveal global geology, the mountains, valleys, and volcanic features that shape the planet's topography. Thermal images show the heat signatures that demonstrate just how extreme Venus's surface conditions really are. None of these images are beautiful in the traditional sense. They're not designed to impress or inspire. They're designed to document reality. And the reality they reveal is more alien and hostile than most people can imagine. The future of hell, the new Venus Armada. After decades of relative neglect, Venus is about to become the focus of unprecedented scientific attention. 3 major missions currently in development will arrive at Venus in the early 2030s, equipped with technology that will revolutionize our understanding of Earth's hellish twin. NASA's VERITAS mission represents the next generation of Venus radar mapping. While Magellan provided our first comprehensive map of Venus's surface, VERITAS will observe the planet with resolution and sensitivity that will make Magellan's data look primitive by comparison. The spacecraft will use synthetic aperture radar to create topographic maps with resolution as fine as 30 meters per pixel, good enough to identify individual volcanic vents, fault scarps, and lava flow boundaries. More importantly, VERITAS is specifically designed to detect changes in Venus's surface over time. The mission will be able to identify fresh lava flows, new volcanic vents, and surface collapses as they occur. By comparing its observations with historical Magellan data, VERITAS will create a comprehensive catalog of recent geological activity on Venus, potentially catching volcanic eruptions and surface changes in real time. ESA's EnVision mission will complement VERITAS with different but equally powerful capabilities. EnVision carries a subsurface radar that can penetrate up to 1 kilometer below Venus's surface, revealing buried geological structures and potentially identifying underground magma chambers that might feed active volcanoes. The mission will also carry spectrometers capable of detecting trace gases in Venus's atmosphere that could indicate ongoing volcanic outgassing. NASA's DAVINCI Plus mission takes a completely different approach. Instead of orbiting Venus, DAVINCI Plus will send a probe directly through the planet's atmosphere, making detailed measurements of atmospheric composition, temperature, and pressure as it descends. The probe will take high-resolution photographs of Venus's surface during its final descent, providing our first clear images of Venusian terrain since the Soviet Venera missions. What makes DAVINCI Plus particularly exciting is its potential to detect signs of current volcanic activity through atmospheric analysis. Active volcanoes should be injecting sulfur dioxide, water vapor, and other gases into Venus's atmosphere in detectable quantities. By measuring these gases at different altitudes, DAVINCI Plus can potentially identify which regions of Venus are currently most volcanically active. The 3 missions will work together to provide an unprecedented view of Venus as a dynamic, evolving world. VERITAS and EnVision will monitor the surface for changes, while DAVINCI Plus samples the atmosphere for chemical evidence of ongoing activity. Together, they should finally answer the fundamental question of whether Venus is still geologically active and, if so, how that activity shapes the planet's hostile environment. These missions represent more than just technological achievements. They're essential for understanding planetary evolution and climate change. Venus provides our only natural laboratory for studying extreme greenhouse effects and geological processes under conditions that don't exist anywhere else in the solar system. The data from these missions will improve our understanding of how terrestrial planets evolve and what factors determine whether a world becomes habitable or hellish. The missions will also search for signs of Venus's ancient past. If Venus once had liquid water oceans, traces of that water might still exist in the planet's atmospheric chemistry or surface mineralogy. Understanding when and how Venus lost its water is crucial for understanding the planet's climate evolution and the conditions that lead to runaway greenhouse effects. Lessons from a dead world. Venus stands as a monument to planetary death, a world that shows us exactly what happens when climate systems collapse beyond recovery. But the lessons Venus teaches extend far beyond climate science to fundamental questions about planetary evolution, habitability, and the future of terrestrial worlds throughout the universe. The most immediate lesson Venus provides is about climate tipping points. Earth's current climate change operates through the same physical mechanisms that once drove Venus's climate collapse. While Earth is nowhere near Venus-like conditions, Venus demonstrates that terrestrial planets can undergo climate changes so extreme that they fundamentally alter the world's habitability. Understanding where those tipping points lie and what triggers them is crucial for predicting Earth's climate future. Venus also teaches us about the role of planetary distance from the host star in determining habitability. The concept of the habitable zone, the range of distances from a star where liquid water can exist on a planet's surface, is partially based on Venus's example. Venus receives about twice as much solar energy per square meter as Earth, demonstrating that even relatively small changes in stellar heating can have catastrophic consequences for planetary climate. This has profound implications for the search for habitable exoplanets. As we discover thousands of worlds orbiting other stars, Venus reminds us that planets within the habitable zone aren't automatically habitable. A world can have the right size, the right distance from its star, and the right basic composition, and still become uninhabitable due to atmospheric evolution and climate feedback processes. Venus also provides insights into the long-term evolution of Earth's climate system. As the Sun ages and becomes more luminous over geological time, Earth will eventually experience the same kind of solar heating that triggered Venus's climate collapse. Current models suggest this will happen in about 1 billion years, but Venus shows us what the ultimate endpoint of that process looks like. The study of Venus's geology reveals important principles about how terrestrial planets evolve over billions of years. The global resurfacing event that buried Venus's ancient geological history demonstrates that planets can undergo catastrophic geological changes that completely reset their surface features. Understanding what triggers these events and how they operate is crucial for interpreting the geological histories of other terrestrial worlds. Venus also serves as a natural laboratory for studying extreme atmospheric chemistry. The planet's atmosphere contains chemical combinations and reaction pathways that don't exist anywhere else in the solar system. Understanding how these exotic atmospheric processes work provides insights that are relevant to atmospheric chemistry on other worlds and even early Earth's atmospheric evolution. The search for Venus-like exoplanets has become an important area of astronomical research. By studying worlds that have undergone similar climate collapses around other stars, we can better understand how common Venus-type scenarios are and what conditions make them more or less likely to occur. Perhaps most importantly, Venus challenges our assumptions about planetary resilience. The planet demonstrates that worlds can cross irreversible thresholds, beyond which recovery is impossible. Once Venus's climate collapse began, no natural process could reverse it. The oceans were gone forever, the surface was sterilized forever, and the planet was condemned to remain hellish for billions of years. This irreversibility is perhaps Venus's most sobering lesson. Unlike other environmental changes that might be reversible given enough time and the right conditions, Venus-type climate collapse represents a permanent transformation. A planet that crosses those thresholds doesn't get a second chance. As we continue to explore Venus with increasingly sophisticated missions and instruments, we're not just studying an alien world, we're studying a possible future. Venus shows us paradise lost, a world that might once have been as beautiful and habitable as Earth, but suffered a climate catastrophe so complete that it became hell itself. The question Venus poses isn't whether such catastrophic climate change is possible. Venus proves it is. The question is how to recognize the warning signs,